Well, now we're going to add and subtract some radicals. Now, if we're going to try to add and subtract radicals, not only does our index of the various radicals have to be the same, index being what we're taking the root of. In this case, everything I see up here is taking the square root, so the index is 2. But also the radicand, what's underneath the radical, must also be the same in order to add and subtract them as like terms. So let's get busy here. So here we got 4 times the square root of 8 plus 3 times the square root of 50. So I'm thinking about, okay, well, in 4 square root of 8, is there a perfect square that I could pull out of there? And there is, because this is be the same as 4 times the square root of 4 times the square root of 2. And let's go ahead and work on this square root of 50. Well, it ends in 0, so I'm already thinking about 5s and 10s. But the square root of, this could also be rewritten as 3 times the square root of 25 times the square root of 2. And you notice here, if I simplify this, well, let's see, the 4 times the square root of 4 is 2, so now we got 4 times 2 times the square root of 2, plus 3, square root of 25 is 5, so times 5, the square root of 2. And now what I have under my radicands are both the same. We're taking the square root of 2. And I can do a little distribution here and then add these. So let's see, 4 times 2 is 8. So we got 8 times the square root of 2 plus 3 times 5 is 15. 15 times the square root of 2. So we're taking both the same index and our radicands are the same. And we can just simply add these together. And 8 plus 15 is 23. And as we add this, we got 23 times the square root of 2. There we go. We've added and subtracted those radicals. Now let's look at this next one. 5 times the square root of 12 plus 2 times the square root of 27 minus 128, square root of 128, excuse me. Well, my index is all the same. We're taking the square root of 12, we're taking the square root of 27, we're taking the square root of 128. And I want to see if I can simplify these to end up with the same radicand, or maybe at least a couple of these 3 terms with the same radicand. So let's go about this. So I got 5. Well, let's see, 4 times 3 is 12. So this could go 4 times the square root of 4 times the square root of 3 plus 2. 27, well, 9 times 3 is 27, so I can write this then as these, and I'm putting these kind of step by step. Square root of 9 times the square root of 23, that's the square root of 27, and square root of 9 is going to be a perfect square, minus 128. Well, if I try to divide 3 in there, that would be kind of my first choice to see if I could end up with a radicand of 3. It's not going to divide perfectly into 128. That's going to be 42 with a remainder of 2. So I'm probably going to, well, I'm pretty well assured right now I'm going to end up with a different radicand on this last term. But let's see if we can pull a perfect square out of there. Well, let's see. What if we divide that by 4? Well, 4 going to 12 3 times. And then I've got 30, and I've got 8. That'd be 32. And 4 times the square root of 32 would work. But I could also divide 32 by 4. That would give me, let's try a different tactic. Let's try 8. Let's see, what might go in there? We got a 4, we know that. That'd be 32. 4 again. That'd be the square root of 8 times the square root of times the square root of 8. Let's see, let me just work this out. I'm going to go first by the square root of 4. So that's square root of 4. What's that going to leave me? 4, that's going to be 32. And I can rewrite the 32 as the square root of 4 times the square root of 8. But you know what? I could write the square root of 8 as the square root of 4 square root of 2. Hopefully that's not too confusing. All right, I'm going to work left to right here. So 5 times the square root of 4, that's 5 times 2 square root of 3, plus 2 times the square root of 9. Well, that's times 3 square root of 3. And then I've got negative. I probably won't put this in parentheses just to keep that negative in front of my face. I got the square root of 2, the square root of 4, that's 2. I got another square root of 4, that's 2. I got another square root of 4, that's 2, times the square root of 2. Well, let's simplify a little more. So we've got 5 times 2 is 10, square root of 3. 2 times 3 is 6, square root of 3. And I'm going to be able to combine those two like terms. But let's go over here. So now I got negative 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 square root of 2. Don't have the same radicand there, so I'm not going to be able to combine that like terms, but I can these two. And so we're going to end up with 16 square root of 3 minus 8 square root of 2. Shazam! Adding and subtracting radicals, simplifying the radical down to where I'm trying to determine, can I get the same radicand? We've got the same index, same radicand. I can combine those. If I don't, then it exists as its own separate term, kind of like x and y, if you will. All right, well, there we go. We're going to move on. And what are we going to do next? Oh, next we're going to multiply binomials that have radicals in them. That'll be a lot of fun.